Welcome back to the Foundry by Forge College. I'm absolutely thrilled to have you here for another explainer. We've been building up some serious engineering muscles lately in our deploying on Solana track. You know, in our last lesson on version control and debugging, we learned exactly how to tag and trace our deployment scripts. But today we're bridging the gap from that perfectly crafted script to the chaotic real world. We're engineering the perfectly isolated deployment setup. So let's get right into environment setup principles. It works on my machine. Ah, yes. Literally the most famous last words in software engineering. I mean, we've all been there, right? We've all uttered this classic excuse, usually sweating bullets, while a script that ran flawlessly on our local laptop suddenly crashes spectacularly in production. And why does this happen? It is always hidden environmental differences. But today, we are going to banish this excuse from your vocabulary forever. Here's our schematic blueprint for today. We'll cover the flaky deployment problem, build an environment layer cake, run through the workflow for reproducibility, weigh some secrets and drift trade-offs, and finish up with our key takeaways. Okay, let's dive right into section 1, the flaky deployment problem. So here is the absolute truth of the matter. Your code doesn't just run in a vacuum. It relies on a massive, invisible web of operating systems and configurations. The root cause of flaky deployments is simply a lack of environment isolation. Basically, the system-level context shifts unpredictably beneath your code. Say your CI runner has a slightly different node version than your local laptop, or maybe the production server is just missing a crucial environment variable. When that happens, you get what we call configuration drift. And make no mistake, drift is the ultimate enemy of reliable deployments. Moving smoothly on to section 2, let's look at the environment layer cake. If we were to sketch out our complex environment architecture, it really helps to visualize it as a highly structured 5-layer cake. At the absolute bottom of this cake is the platform layer. This is your foundational operating system, your kernel, or maybe a specific Docker base image. It sounds so basic, but subtle differences down here can literally be lethal to your app. Just a tiny OpenSSL version mismatch at this base layer can cause maddening TLS handshake errors when your script tries to talk to a Solana RPC node. If your foundation cracks, everything above it completely falls apart. Now, sitting just above the platform, we have the runtime and dependency layers. The runtime layer is exactly what language binary you're using, like a strictly pinned version of Rust-C or Node.js. And right on top of that are your dependencies, which are locked down by files like cargo lock. You know, these layers require incredibly strict pinning to keep your dependency graph from crumbling under pressure. If you don't lock these down, a simple library update can completely alter your script's behavior overnight. So above those dependencies, we have our configuration layer. That's your environment variables and feature flags. And finally, the icing on the cake, strictly separated from everything else, secrets. We're talking cloud KMS keys or vault credentials. Together, this entire stack acts as your ultimate troubleshooting map. When a deployment inevitably fails, you just work your way down. Is it a bad secret, a missing end variable, a corrupted lock file, or did the base image change? It's all right there. All right, section 3, workflow for reproducibility. So how do we actually bake this reproducible cake? Well, it's a super reliable 4-step workflow. First, define the environment's purpose. Is this local dev, staging, or production? That alone dictates your security posture. Second, you capture all those layers we just discussed as declarative artifacts. Third, you generate an immutable build. And fourth, you strictly verify it all with automated smoke checks before it ever goes live. Let's zero in on step 3 for a second, the immutable artifact. This is a digest, pinned container image or a VM snapshot that acts as a permanent, completely unchangeable anchor. By treating your environments as immutable, you guarantee that the exact image tested and approved in your CI pipeline is the exact same image deployed to production. No last-minute tweaks, no live patching. It is totally locked in. And before that immutable artifact is allowed anywhere near production, it has to pass step 4, the smoke check. Think of a smoke check as your safety valve. These aren't deep unit tests. They're quick, automated sanity tests that validate critical behaviors. In Web3, this means verifying your script can actually parse a wallet key without accidentally signing anything, or ensuring it can establish a stable connection to your Solana RPC endpoints. It basically proves your environment is actually capable of performing the deployment. So where does all this stuff actually live? Well, every artifact has a designated home. Your base images go into a container registry. Your configuration files belong right next to your code in a versioned repo, and your secrets absolutely, positively must go into a managed secret store. Keeping this structure maintains the pristine traceability we established in our last lesson.
Let's move into Section 4, Secrets and Drift Trade-offs.
In engineering, it's always a balancing act, right? You have to balance aggressive pinning against relaxed pinning. Aggressive pinning, where you lock down every single hash and version, is fantastic for rock-solid production environments, but it can severely slow down security patches and frustrate your developers. On the flip side, relaxed pinning keeps your local devs moving quickly, but it opens the door wide for that dreaded configuration drift. The sweet spot? Pin strictly in CI and production, but allow a little more breathing room for local development, backed by automated dependency scanning.
And when it comes to that top layer, secrets, the trade-offs are even more intense. Embedding secrets directly into your images or code might simplify your runtime setup, but it creates massive, unacceptable security risks. Basically, anyone with access to the image has the keys to the kingdom. No way. Using a managed secret store like Vault or Cloud Canvas is absolutely the right way to go. Sure, it requires network access to fetch them at runtime, but it gives you essential audit logs, revocation, and rotation capabilities.
To manage all these trade-offs without losing your mind, you need strict operational rules. As you take more of Forge College's Web3 engineering courses, you'll learn exactly how to implement automated CI enforcement rules. You want to require peer reviews for any changes to environment manifests. And, most importantly, you want your CI to completely block any code merges if those smoke checks fail. You have to stop configuration drift dead in its tracks before it ever hits the main branch.
Okay, we made it to Section 5, Key Takeaways.
Let's wrap up our technical blueprint here. If you remember nothing else from this explainer, please remember this. Treat your environments as versioned artifacts, not as anonymous machines. Always pin your low-level layers, keep your configuration explicitly versioned in the repo, lock those secrets safely away in a vault, and automate your smoke checks. But even with perfect pinning and secure vaults, a pretty massive question remains about our testing contexts. You are now fully equipped to build unshakable deployment environments. Get ready for our next lesson where we'll actually dive hands-on into provisioning dev environments. To master Solana deployments and expand your Web3 expertise, be sure to check out forge.college. But before you go, I want to leave you with this provocative thought. If your testing context in CI doesn't strictly mirror your production reality, is a passing smoke test just a comforting illusion? Think about it, and I'll see you in the next explainer.